Welcome back, guys. Let's do one more example of Newton's method. This is going to be example 3. This is also number 3.34 if you're following along in the actual textbook that I use for this class. Now, this problem, we've got an ice cream right here. All right, and we've got a couple of h values. So h right here, the little h is basically the height of this cone, and then the capital H would be the height of the actual ice cream that's sitting on top. And then r is the radius. We're going to assume that this is like a perfect sphere here for the ice cream. Now, we're also given the volume equation for the ice cream, and you can see it here. It's a function of h, both h's, so little h, capital H, and then r. And what we want to do is we want to find the value of capital H, so this height right here of the ice cream, if the volume is 1/3 of a pint, little h is 4 inches, and the radius is 1.1 inches. Okay, so that's what we're looking for. We're looking for h. And we can use Newton's method to solve this because we're wanting to solve this equation for one unknown. All right, and we can rewrite this equation. So let's rewrite the equation so that we can use Newton's method. So remember, with Newton's method, everything has to be set equal to 0. So right now I've got volume over on this side. So if I bring that over and put everything on one side, I'll have my function, we'll just write function of h, and then that's going to equal pi times r squared times h over 3 plus r squared times capital H over 2 plus h cubed over 6. And then we're going to subtract that volume, set it equal to 0. Okay? Now this is the right form for Newton's method. All right? Everything is set equal to 0. Now, basically, the root that I'd be finding would be h. So we want to find the value of h that's going to make this equation go to 0. That's what we're looking for. Now, before we go to MATLAB, we're going to solve this in MATLAB. Before we go over there, we need to find the derivative function because we need that for Newton's method. Now, to do that, you got to think of which variable we want to look at. So for that, what you need to do is know what variable you're trying to solve for. So we're trying to solve for capital H. That means when we do our derivative function, I want to take the derivative with respect to capital H. All right, we don't care about r and little h. Those are constants, right? Those are right there. So that's not what we care about. We care about the capital H. So when we do our derivative, we'll have pi times, we'll look at this term, r squared over 2 plus 3h squared over 6. All right, and those will be our two equations. So this part right here on Newton's method, this is the one that typically kind of trips students up sometimes because they're not sure what variable to use. But just remember, you're going to take the derivative with respect to the variable that you're trying to solve for. That's what you're trying to do. Okay? So now let's switch over to MATLAB. We'll put this in and then see the solution that we get. Here we are in MATLAB. Now this should look familiar to you. It's basically the same setup we had from the last example when we went to MATLAB. So all we've done is pretty much kind of adjust things for this problem. First thing we need to do, let's define our constants. We've got our little h, which was 4, r was 1.1, and then we had volume. We were told that volume was equal to 1/3 of a US pint. All right, well, pint is typically not going to be a unit that we want to use. We had inches for these other two values up here. So I want to convert over to inches, and here is the conversion right here. So 1 pint equals 28.875 inches cubed. So I just took that number divided by 3. All right, so that gets us in the right units. And then we set up our equations. So here's our f of h equation. It's just like what we wrote down on the paper. And then here's our derivative equation. So now that we've got our two anonymous functions set up, we can go ahead and get started. Now on this problem, you weren't given really a tolerance or an initial guess. Those weren't given. So for this one, I did an f-plot here just to kind of show you how you could do an initial estimate for your initial guess here. So we'll do f-plot f and then see what it gives, and then you'll notice I'm just going to choose 1, and then we've got our tolerance. I just set it to 10 to the negative 6. Seemed like a good number. And then here's our max number of iterations. And then we call the Newton's function, which has not changed from the last example. And then finally update f(f) so that we have h here, because h is what's being returned from that function. So let's go ahead and run this. Alright, so there we go. I was waiting for that figure to pop up, but it didn't pop up. But here it is. So here is the function plotted. That's what it looks like. So I'm wanting to find where we're crossing that x-axis. So it's over in here somewhere. So that's why I just assumed 1 would be a good choice. Alright, because here's 1, so that would be a good choice. Alright, so I picked 1 right there. Got our tolerance. And then let's see what we get. Here is the solution. Okay, so capital H, or the height of that ice cream, is going to be 1.488614 approximately. And you can see how the Newton's method iterated. It kept updating that initial condition, that initial guess, until we got down to this point. If you come over here, you can look at your tolerance, your function values, and you can see they keep getting smaller and smaller, and then eventually we settle in on that value right there. Alright, so that's how that one is set up. So hopefully that makes sense, and that'll be our last example for Newton's method. We'll switch to a new method in the next video. Thanks guys!